So we're going to take a look at the Unit 1 review worksheet. I'm in the digital course pack for winter, and we're headed to page 110 through 160. Let's try this. I'm going to hit Control F. Hello, let's try again. Control F. There we go. And I'm going to type in Unit 1 review. Review B. And hey, look, it found it. So this is the one that you're going to turn in. Did I say Unit 1? We're already on to Unit 2. I got to grade your Unit 1. Let's try again. There we go. Unit 2 Review B. This is one that you're going to turn in, the Walmart Nacho Cheese Doritos problem. So the practice one is the Unit 1 Review, Unit 2 Review A. Okay, here goes. Oh, good gracious. I got to do that again. Unit 2. Why don't I just type 1? So on my, this is a 2A. You might be thinking I should just restart this video, but I think you might get a laugh at my ridiculousness. Okay, so I'm clicking in here. There we go. Now I want to close this out. And let's see if my tool works. So the first, here, this is the table of the average yearly income for a factory worker with 5 years of experience. I don't know where this data came from. May be true, may not be. Let's notice a couple things. First off, we're told that we are doing this as years since 1990. That means 1990 is going to be our zero value. That is way too thick. Come on now. And then 1991 would be a 1, and 92 would be a 2, and a 3, and a 4, and a 5, and a 6. Now, if you have more challenging numbers to figure out that aren't nice in a row like this, what you would do is take the year that you're at, so let's say 1996, and to calculate that value, you would subtract from it the year that we started, the 0 year value, which is 1990 in this case. So you can see that our value was right. 1996 minus 1990 is a solid 6. So then we're supposed to draw the scatter plot. And really, we should be labeling the x and y axes, right? So the x-axis would be labeled as years since 1990, and the y-axis would be income. And then we should note that it's in thousands of dollars. So these factory workers in 1990 were not making $35.2 or $35.2 dollars a year, because this is average yearly income. They're making $35,200 a year. So graphing here, okay, so x-axis isn't bad, right? 0, 1, 2, 3, etc. Y-axis is a pain. I guess we could do 10, 20, 30, 40, 50, and that's all the more we would need. And 0, 35.2 would be something like this, and I'm quickly losing the desire to graph this. 1, why didn't it plot? That's another thing I wouldn't like. For some reason it didn't show up. And then 2, something with my computer, something like this. Okay, so it looks something like that. What we really want is to go to Desmos. So let's pull up Desmos. And let's get the actual scatter plot of this, not our hand-drawn best approximation of this mess. So recall from all the stuff we've done, if we're putting in a table data, you add an item with the plus sign, pull up your table, and then just type in your stuff. Ooh. 1, 2, 3, 4, 5, 6. Good practice in counting, and then 35.2, 37.1, 39.4, 41.8, 43.1. Now, if you think counting is a really simple thing, that's great. But talk to a 3-year-old about counting, and you'll get that it's a skill that you learn. So if you think you're bad at math, but you can count, think again. You learn that. If you can learn that, you can learn anything in math. Come on now, right? So I'm hitting the zoom fit. Now, let me double check my numbers. 35, 37, 39, 41, 43, 40. Yeah, this looks approximately linear. So this question of C, what does the scatter plot tell you about the average yearly income? Number one, it's increasing. So it's increasing over time. And it appears to be linear. So it appears to be a constant increase. Thus, it's a linear, probably modeled by a linear function. Definitely doesn't look exponential. Now, it's not exactly linear, right? You can see this little bump right here where it kind of had a steeper slope, and then it went less steep, and then steep again. Okay, so number two, we've got that this Lime scooter rental rents out electric scooters for initial cost. Ooh, keyword, right? We should immediately know what this is. Initial cost, that's starting value. That's when x is 0, y is 1. That's the y-intercept. So initial cost and 10 cents per minute after that. So $0.1 per 1 minute. Now, what we have to decide is, does this represent a exponential growth, decay, or linear growth or decay? So 10 cents per minute sounds like a constant change per 1 unit time, where that unit time is minutes. This is not a percent increase or percent decrease, which would clue us into exponential models. So this is definitely a linear model. And here I'm doing all this talking, and look, it tells us linear model. But I did that talking because there's going to be problems where we don't give you that clue, and you got to figure it out based on the types of numbers given. Well, since I've identified this as the y-intercept, I know what my b value is, and I know what my m value is, and I know that a linear model or a linear equation, one form of it is the slope-intercept form. So all I have to do is substitute in the things we've been given. 0.1x plus 1. These units are in dollars, and this unit is in minutes. So we're spitting out minutes as well. I'm sorry, this unit is in dollars per minute. So when we multiply, wrong. Let me try again. I was right the first time. X is in minutes, and this slope is dollars per 1 minute. So when we multiply minutes over 1 times minutes, they cancel, and we're left with just dollars, which is what we want y to be, total cost. So then we got, how much will it cost to rent the scooter for 35 minutes? Well, this is an x value in minutes, so that matches what our value here states, and we can find the cost using our model. So 0.1 times 35 plus what? Notice I've gotten lazy with my units. You know what? I shouldn't be lazy with my units. Let's put them in. There's that. So using our lovely dimensional analysis, those would cancel out. And we're left with, let's see, $3.50 for the 35 minutes plus the dollar, $4.50. Man, that's a cheap rental. This is definitely back in the 90s. Come on. All right, so how long can you rent the scooter if you only want to spend $15? Well, notice that's the units on that is dollars, so that tells us we're definitely in the y equals value. And what we want is the x value. How many minutes is this? All right, well, we'll use our equation again, $15. That's going to equal the $0.1 per minute. Look at me not being lazy. Times x plus $1. So we can solve this by hand, or we can use Desmos to solve it and solve it graphically. Either way, I'll go ahead and do both. So I'll solve it by hand first. I'm going to subtract the $1 from each side. So I've got $14 equals 0.1 times x. At this point, I'm going to ignore the units. And I'm going to divide both sides by 0.1. Dividing by 0.1 is the same thing as multiplying by 10. So we can rent this thing for 140 minutes. Great. Let's check out Desmos with this. So in Desmos, all we would do is type in our equation, y equals 0.1x plus 1. And then we want to see, when does y equal 15? So let me hide our table here. And let's get back to our home screen. Here's the y equals 1. Here's the 15. So it's quite a ways out there, right? We got to zoom out a bit. There we go. Where these intersect, the x value is the solution. And note, there's 140 minutes for x. There's our $15 for y. That would be our graphical approach for solving question C. let's check out question 3. So Comcast, that's my internet provider, estimates the number of households in millions Y with internet access to be modeled by Y equals blank, where X is the number of years, Y is that mess. So this Y represents households, and all the numbers we get are in millions of households. So what's the slope? Well, recall that our equation, our general equation is Y equals mx plus b, right? So if I look at the equation they've given us, why don't I just write it down? Notice that the m, or the slope, is the number times x, and the b, or the y coordinate of the y-intercept, is the number by itself. So what's our slope? That's m equals 6.76. And what is this? It's households per 1 year. That's the units on this, because x is given as years since per 1 year, so I need to add per 1 year since 1990. So what does this mean? Since it's a positive value, and we're representing houses with internet access, we're going to say the number of households with internet access, oh boy, I'm running out of space, has increased by 6.76 million per year since 1990. That's the interpretation of the slope. Notice all I did was identify what the y value was, which is the top of the slope. That's delta y over delta x, and what the x value was, which is the denominator or the bottom of the slope number. Most often our equations are given in decimal, so that means our denominator is always a 1 unit. So these are all unit rates. All right, then we're supposed to identify the y-intercept. Now you should be very careful. When you're asked to find the y-intercept, that's an ordered pair. Right? It's not just the 14.9, and we should note that this is in millions. Okay, what does this mean? Well, since 0 is an x value, this means 0 years since 1990. I think the appropriate English word here is in 1990. There were 14.9 million households with internet. I should probably put in here that it's important to keep in mind that both of these values, the slope here and this y-intercept here, both of these statements are statements that we've drawn from the model. So they're approximations of what we believe to be happening. It's quite possible that in 1990 there was a much different value, if you recall from some of the problems we've done in the course. Okay, so according to the models, how many had internet access in 2010? All right, that's an x value. We need to know what is the x value we're going to plug in, so we got to subtract 1990 from it. That feels like a solid 20. So we're just going to plug that in. Y equals 6.76 times 20 plus 14.9. Whatever this number is what our model approximates it to be. I don't know if that's good English. Let's see, 20 plus 14.9. There it is, 235.924 million households. Let's make sure I have that memorized. 239.924 million households. That's what our model believes it is. All right, and then according to the model, in what year would the number of households with internet reach 100 million? Notice this is a y value. So we're asking, when is this, for what x value is this thing equal to 100? As before, we can solve this by hand. So we can subtract the 14.9 minus 14.9. Oh boy, do I want to do this in my head? Maybe. So if it was 15, it'd be 85. So this would be 84.1. No. Maybe 85.1. Okay. And then we're going to divide both sides by 7.6. and by that I mean 6.76. And so x is whatever this is equal to. Now I'm going to rely on Desmos to pull that one off. What did I say? 85 point, split screen this bad boy, 85.1, come on now, 85.1 divided by 6.76, and we get an approximation here. This is approximately, okay, easy killer. Oh, what's going on here? Approximately, I'm going to click back to this, approximately 12.5, let's say 12.6 years. So this is 12.6 years after 1990. Notice Amano said in what year. So this is not the answer. That's not a year. Well, I guess it is 12.6 AD or whatever that other one is. But that's, there was no internet back then, obviously. So we'd add this to 1990 and we'd get 2012.6, which isn't a year either. So we could say either in 2012 or 2013 if we were rounding somewhere within there. All right, so let's do number 4, and we'll take a break, okay? So Meijer is having a sale on 2 liters of Coke for $1.67. Wonderful. What's the unit price? All right, this is a special word. Remember, unit price means denominator of 1. So we should have something over 1. And notice how we are to find this. It's dollars per liter. So dollars over liters, 1 liter. Well, here's the quantity we've been given, $1.67 over 2 liters. To turn this into a unit price, all we have to do is do the division. So what is 1.67 divided by 2 equal to? Turns out that's a solid 0.835. Now we want to write this as a unit rate, so $0.835 per 1 liter. That's what it is. So what does this mean? The cost of 1 liter, or let's say it this way, it costs $0.835 for 1 liter. Liter, yeah, it looks wrong, but I guess it's right. All right, then you see 12 packs of 12-ounce cans on sale for $3.50. What's the unit rate in dollars per ounce? All right, notice we've got $3.50 is the cost. And we're supposed to do this per ounce. So this is divided by 12 ounces, but there's 12 of those, right? So we'll put 12 ounces times 12, which really, I know what 12 times 12 is from back in the day. That's this, but I'm not quite sure what that is in division. So let me grab Desmos again. And we're doing the good old 350 divided by 144. That's 0.02. How many decimal places do we want? Let's just do, I guess let's just do 0.02 per 1 ounce. So 2 cents an ounce. Obviously, we're going to ask you which is the better deal. Which should you buy? Boy, those 2's look a lot like my Z's, don't they? Let's put a line through the Z so we can see a difference. So if there are 33.8 ounces in one liter, what sale is the better deal? Well, so we have a choice. Do we want to convert this cost per liter into cost per ounce, or do you want to convert this cost per ounce into cost per liter? Good news, I'm going to do both. So we'll take the 0.835 divided by 1 liter. And since I rounded this to 3 decimal places, I'm going to go ahead and round my other number to 3 decimal places. So it's 0.024, so we're kind of comparing a little more equally. This is per 1 liter. So if I want to convert this thing to ounces, I want the liters in top with this equivalency statement. In other words, this statement, 33.8 ounces in 1 liter, means 33.8 ounces equals 1 liter. Multiply this out, and we will have converted this thing into dollars per ounce. Simultaneously, going to convert this one, so 0.024 over 1 ounce, into dollars per liter. This time, I need the liters in the bottom and the ounces in the top. Ounces cancel, blah, 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 away we go. So let's split screen this. The old computer can handle it. And we need 0.835 divided by 33.8. Okay, so this is, oh, look at how close this is. This is 0.02470,414 ounces per 1 liter. Now remember, we rounded this to 3 decimal places, so maybe we should include a little more of these when we do our comparison. So I'm going to add in a few more digits for that one. And then I will take the 0.0243006 and we'll multiply that times 33.8, and there's our value per ounce. So 0.8215 dollars per 1 liter. Okay, so now we just have to figure out which is the better deal. Well, hopefully it's pretty clear to you that they're really stinking close, right? So we had to go to the, in terms of dollars per ounce, we have to go to the 10,000th of a cent to find a difference. And so the 12 pack of 12-ounce cans is cheaper. Is it better for the environment? I don't know. Which is worse, plastic or aluminum? I guess they recycle. Well, they recycle both, don't they? We do here, and we also pay for that. So maybe it's negligent. I don't know. And then we could also look at the liters, and this was not a rounded value. And you can see it's a little more striking of a difference here in terms of this value. So you can think about, we've done 33.8 ounces of this mess. Now we also we used this many decimal places for our calculation here. So it's we actually made it a little more expensive because we rounded this to a 6, but not enough to be significant. So it's almost a cent cheaper per ounce, per liter. So the 12 cans is the best option here if we're looking strictly at cost.